Well, it's good to be with you again today. I hope that you're ready for another day of geography. Let's go ahead and get organized. Today you're going to need activity 3.1 for your materials. That's going to be part of your assignment. And 3.4, you can fill that in during the lesson. There's a section on water distribution. And today we're going to be looking at wind review. So we'll start with that, a little bit of review on the wind. And then we'll move from there to ocean currents and El Nino, which has to do with distribution of heat. And we'll also be talking about the distribution of water and a couple really simple, easy water demonstrations, or at least one. All right? Our main idea for today is also simple, one that you've probably learned many years in the past and heard many times. It's that water is spread throughout the earth by the hydrologic cycle. So hopefully that'll be easy review for you. Your goals today are to explain the basic cause of ocean currents, identify the elements of the hydrological cycle, and distinguish the three situations that produce precipitation. Let's go ahead and start today with our chapter verse. So read this along with me. Our chapter verse is Genesis 8:22. While the earth remaineth, seed time and harvest, and cold and heat, and summer and winter, and day and night shall not cease. All right, let's get right to our review on the wind. This is a listing review. So you want to list three factors that affect wind. Can you name them off quickly? Okay, latitude, remember where the air drops down and cools, rotation of the earth, or the Coriolis effect, and the heating and cooling of the continents had to do with our high and low pressure systems. Can you list the three wind belts? The basic ones are the easterlies, toward the polar regions, the westerlies, and the trade winds. Can you remember the three calm areas between wind belts? All right. The most important to remember are the doldrums near the equator, and then the horse latitudes around 60 degrees. And also we have the subpolar lows. All right. Which illustration shows the wind belts? Can you choose the correct illustration? It's the one on the right, shows all the wind belts that we talked about. The easterlies at the poles, then we have our westerlies and our trade winds there near the equator. Okay, which illustration shows the Coriolis effect? Again, it's the one on the right. Remember that the wind blowing toward the equator is veering to the west, and the wind blowing away from the equator is veering toward the east. All right, so I hope that you remembered those facts about the wind and the patterns that we studied last time. And hopefully you'll find ocean currents maybe a little easier than the wind belts that we talked about earlier. Now, so far in this chapter, we've been dedicating our time to heat in motion. We started with the seasons, and then we moved on to the winds in our last lesson. And the ocean currents also help in the distribution of heat around the earth. So this is kind of a part of our last section that we didn't get to, and I just went ahead and moved it over into this section on water today, since it does have to do with water. Now, water-specific heat, that's the capacity to store heat, is one of the highest known in the universe. And this is just another example of God's wisdom in the creation of this molecule. We talked about how he wisely balanced how much water is on the surface of the earth compared to the land, but also just the creation of the molecule, how when it freezes, it actually expands so that it floats, so an ice layer is formed on the top, and the animals and vegetation can survive. They're protected from the cold weather, but also the specific heat capacity. Just another illustration of God's wisdom. But what does that mean for our discussion? If water has a greatest capacity to hold heat, a very great capacity to hold heat, it means that the water actually absorbs the heat more slowly than land, but it's going to retain the heat much longer also. And last time we learned that the continents absorb and release heat much more quickly than water. We learned that last time. And this allows the hot air masses to form over continents in the summertime. And we want to take a look at this in your textbook. This is a little bit of review, but we didn't get real detailed on it last time. This is some common high pressure systems in July, and I want to take a moment to look at the map and just answer a few questions about it. So scan over it, get your bearings on it. All right, which continents have a low pressure system? Which continents have a low pressure system? Actually, it's clear to see the one in Asia, but there are two that are near North America, so these are considered to go with North America. Part of the low pressure system is indeed over North America. Let's look at the one, since this one's easy to see, right on the continent of Asia. We'll use it as an example. Remember that it's summertime, the land heats up more quickly than the water, so we have a low pressure system here as the hot air rises. Remember, it creates a sort of, as it rises, it's kind of creating a little vacuum and pulling the air in. Notice all the air is going toward the center of the low pressure system. It's drawing the air into the interior of the continent. Also, we can notice the Coriolis effect on the direction of the air. Remember that our air going toward the equator is going to veer west, and away from the equator, you can see these arrows, it's going to veer east. So if it's going toward the equator veering west, like these arrows are, away from the equator veering east, we have a counterclockwise motion, don't we? And that is the motion of the low pressure system in the northern hemisphere, counterclockwise. And notice that all these other lows, we don't need to talk about them specifically because they're also in the northern hemisphere, so they're also going to be moving counterclockwise, and you can see that by the arrows there. All right, now which oceans have high pressure systems? Just take a glance real quick. And did you notice some have two? Why do some oceans have two high pressure systems? What do you think? Well, we can see right away that the Pacific, the Atlantic, and the Indian Oceans are the ones with the high pressure systems. We see that the Pacific and the Atlantic both have two high pressure systems. It's because of the areas. Notice there is no Indian Ocean up here. This is where the high pressure system would be if the Indian Ocean were larger. But they match up with our high pressure systems in our wind belts. Just pull this in from the previous page. Notice our high pressure system here between 60 and 30 degrees latitude, and also a high pressure system here between 0 and 30 degrees latitude. And those are going to match up. So that's why they have two high pressure systems. Okay? And you might have also noticed that all of the systems over the oceans are highs. Now remember, the highs are pressing down. The air is going to be probably cooler over the oceans because it takes longer for the water to absorb the heat, and the high pressure systems are going to be pushing down and pushing air away from them. So when we take a look at them in the northern hemisphere, pushing the air away, we notice again the Coriolis effect. Air going away from the equator is veering to the east. Air going toward the equator is veering to the west. So we have a clockwise motion in the northern hemisphere on the high pressure systems. Look, however, below the equator. Remember, we have two high pressure systems because both oceans have water in the middle latitudes. Below the equator in our southern hemisphere, remember, the wind going toward the equator is veering west, and wind going away from the equator, as you see here, is veering east. Notice what direction that makes our system going. It's counterclockwise in the southern hemisphere. You might have learned that before, like cyclones and hurricanes and things go counterclockwise, depending on whether it's a high or low system, of course, as well. All right, so that's where we notice the Coriolis effect. Some systems go, the northern hemisphere going clockwise, the southern hemisphere going counterclockwise. All right, a few more questions. What direction are prevailing winds blowing in South Asia? And what direction will they blow in December when high pressure systems develop over the continent? You might need to pause the program to work on that. All right. Let's look here. Here is South Asia. We see that we have a low pressure system, so it's going to be traveling counterclockwise, or the direction of the wind is actually this direction, so it's to the northeast, toward the northeast. In December, if it's a high pressure, it's going to go the opposite direction like this high pressure does. And so our wind is going to be blowing this direction, which is southwest. All right. Now, because the oceans hold heat so well, they're actually more important in the distribution of heat than the winds are. And the ocean follows this, the water in the ocean follows a pattern similar to our basic wind pattern that we talked about previously. I just want to show you on the globe. It's the real simple pattern. All right. Now think about the water at the equator. That's where the sun's most direct rays are, right? And so this water is going to warm up and it'll become hot, right? So it's going to rise. There's currents in the water just like in the air. It's going to rise and it's going to flow toward the cold poles. So it's really going to be doing both ways. At the poles it'll cool and sink and travel back to the equator. So we have that same basic cycle going on that we have with our wind patterns, all right? And I'm showing you above, but you can just imagine it's the same thing that's happening with the water. It's actually the water, just like our basic wind pattern, where the air warms and flows towards the poles. Now, the patterns of the water are simply called ocean currents, and you've probably heard that term many times before. They're the basic paths of water that flow within an ocean. They are warm and cool. That's how we typically refer to them, a warm current or a cool current. Generally, they travel less than 10 miles per hour, but some get up to over 60 miles an hour. Some currents are very rapid. The slowest currents are called drifts. They just, if you got in a slow current, you would just kind of drift along. And we use the term gyres. These are circular patterns in which the currents flow. So with the wind, we had wind belts or prevailing winds. With the ocean, we have currents or gyres. So what we want to do is look at some major ocean currents in your textbook. And this is on page 45. The major ocean currents, and you can see that they are color-coded here. The cool currents are blue and the warm currents are red. So let's answer the Go Exploring questions at the bottom of the page. You might want to jot some of these down just so you have for reference. Okay? What warm current begins in the tropics of North America and ends near Europe? All right, here's North America. Here's our Tropic of Cancer. If we follow along to Europe, that's going to be the Gulf Stream. The Gulf Stream. Do any warm currents flow past the west coast of South America? All right, here's South America. Here's the west coast. We have the Peru current, and blue stands for cold, doesn't it? So there aren't any warm ones flowing here near the west coast of South America. Now, can you list all of the named currents in the Pacific Ocean and then tell which are warm and which are cold? Not that many, so it shouldn't take you too long. Okay, if you're writing them, you might need to pause to write them down, but you should have been able to locate them by now. They're pretty easy to see. We have our California current, equatorial current, Peru current. Don't forget, did you remember that the Pacific Ocean is also over here? We've split it on this map. We have the Japan current and the East Australian current. The cold ones are California and Peru, and the warm ones are equatorial, Japan, and East Australian current. Okay? Now, here's the thought question. You're going to have to think a little bit on this one. Can you guess the currents that Magellan's ship followed from Europe on the first trip around the world? So you're going to start in Europe and then try to follow the currents all the way around the world. And I'll give you a little hint. One of the currents isn't actually labeled. It's shown there, but it's not labeled. So you'll just have to, jot that one in. Okay? All right, did you make it around the world? Let's check and see. We'll just follow some of the currents that are marked here on this map. Starting from Europe, we'll catch the Canary Current taking us down towards South America. Then we want to get the Brazil Current taking us to the tip of South America. We want to avoid this current traveling east and get up here to the Peru Current carrying us up the west coast of South America. From there, we want to catch the equatorial current that's traveling west. Notice there's an arrow going both ways there to the west. And from here, we will take the northern Indian Ocean. And this is the one that's not actually labeled. I believe it's this one right here. We're in the Indian Ocean to South Africa. From there, we want to catch the Benguela Current up the coast of Africa, and then we'll have to just sail from there back up to Europe. All right, so that's a basic pattern that Magellan could have followed, although it was many years before sailors realized and understood about the ocean currents and could use them they could use them, but they didn't know all of them or understand all of them for a long time. Now, there is a phenomenon known as El Nino whose origin has been traced to some unusually warm currents in the ocean. Let's take a moment to learn about it.
Good evening. In today's news, farmers are preparing for the predicted El Nino season. Tina Gurney has this special news weather report. Tina?
Farmers are only one of the groups around the globe who are preparing for El Nino. El Nino refers to a weather episode occurring in the tropical Pacific Ocean beginning near the Easter Islands. It's kind of like its own season, except that it doesn't have a regular cycle of coming and going, like the 4 seasons the U.S. experiences. El Niños occur at anywhere from 2 to 7-year intervals, as do La Niñas, the sister companion of El Nino. La Niña refers to unusually cool changes in sea surface temperature, bringing about opposite weather conditions than El Nino. What happens during El Nino is that normally high air pressure in that area of the Pacific Ocean drops, so the trade winds die down, the water becomes warmer, and begins moving eastward. As these warm waters keep moving throughout the ocean for some 12 to 18 months, normal weather patterns for much of the world are altered. Just how does El Nino affect the world? Droughts, floods, storms, and tornadoes are some of the weather phenomena attributed to El Nino. This affects those who manage water, energy, and transportation, also farmers and those involved in occupations related to things like fishing, forestry, energy, and agriculture. Ted?
Well, Tina, when can we expect the next El Nino?
Since El Ninos don't occur on a regular schedule, scientists try to predict their occurrences, so those who could benefit or be harmed by weather extremes can plan ahead. Back to you, Ted.
Thanks, Tina. El Nino is Spanish for the little one, a name coined by the residents of Peru and Ecuador to refer to the regular occurrences of warming ocean waters off their coasts at the end of each year. The El Ninos we refer to are only the extreme warmings of the ocean waters there that have worldwide effects. In sports news, national football takes a wild throw from the Victoria.
Well, that gives you a better idea about El Nino, and it is difficult to define it briefly, but let's try to think of it like this. It's a phenomenon that occurs when waters in the Pacific warm up and move east and north, changing weather patterns. All right. Now, looking at the ocean currents reminds us that water is constantly in motion, and that is our topic for this next section that we're getting into. Psalm 135:7 tells us, "He causeth the vapors to ascend from the ends of the earth. He maketh lightnings for the rain. He bringeth the wind out of his treasuries." And before we go any further into our topic of water in motion, we're going to start a little demonstration. This is something very simple. You've probably seen it many times before, but I just have a little bit of ice here in a glass. I'm going to pour it full of water, and we'll check on it later. Hopefully we'll notice some water in motion just from that simple glass. Now, much of this next section should be review for you. So we're going to start with the different states of water and see what you recall. First of all, we have the 3 states of water. Do you remember them? Okay. Solid, like ice, liquid, and gas, as in water vapor. Now, do you remember the process of water changing from a solid to a liquid? That's melting. A liquid to a solid. Freezing. Liquid to a vapor. Evaporation. Okay, what about from a vapor back to a liquid? Condensation. From a solid to a vapor, this is an unusual one, known as sublimation, and also from a vapor to a solid is referred to as sublimation. Now, sublimation might be a new one to you, but that occurs when a larger amount of heat is released or absorbed. For example, when water vapor comes in contact with a cold glass, it forms frost. And here's a glass that I've just taken out of the freezer, and you can see that it's all frosty. I can kind of touch it. You ever do that in the wintertime? Touch it, and you can kind of make a little, see, now you can see through it a little bit. But that would be an example of sublimation. However, sublimation is less common than the other processes. Now let's look at some other related terms and see if you recall any of these. Humidity is one that we'll be working with. That's the amount of water vapor in the air. Dew point might be a review. That's the point at which water begins condensation. And then, of course, I'm sure you're familiar with precipitation. That is the fall of water to the earth. And just some examples: rain, snow, hail, and sleet. Now, God has established a water cycle to help sustain life on earth. In Job 37:6 we read, "For he saith to the snow, Be thou on the earth, likewise to the small rain and to the great rain of his strength." And this cycle is also referred to as the hydrologic cycle. And that's simply a pattern in which water is continually moving back and forth from the earth to the atmosphere, from the atmosphere to the earth, and it helps replenish soil, plants, lakes, and rivers. It comes from the term hydrology, the study of water, and hydro means water. You can think of hydroplaning on the water, and of course, logy means study, like as in biology. Let's see what you remember about the water cycle. You should have studied this previously. First of all, let's do the processes. All right, starting with the lake water going up into the air, that's going to be evaporation. Also, water vapor is released through leaves and stems and flowers. Do you remember that term? It's a little less common. Transpiration. Respiration as well, but it's not shown on this diagram. And then the water condenses in the clouds and falls to the earth. We don't have condensation labeled here either. It wasn't in your textbook. But the precipitation is when the water falls to the earth. Then we have some water that drains from the land into the lakes and rivers. That's entitled runoff. Some goes into the soil, simply called soil water, and some seeps deep into the ground to underground rivers, and that's referred to as groundwater. All right, so let's recap quickly what our hydrological cycle is. You can start anywhere because it is a cycle. Evaporation, transpiration, and respiration. You don't have to remember respiration. From there to condensation, it condenses to water droplets. And let's take just a moment to check our glass. We have a little bit. I'm not sure that you can see it, but we do have some condensation. A lot of times we just call it sweating. This is why your mom wants you to use a coaster instead of putting your glass on the countertop. But we just have condensation forming around the edge of our glass. So from condensation, it forms little water droplets, and then from there, those droplets fall to the earth, which is precipitation. All right. Now, there are some areas that rarely receive rain, but they're able to support vegetation just through mist and dew. All right. 80% of the precipitation that falls to the earth falls over the oceans, and of course the other 20% falls over the land and becomes soil water, runoff, and groundwater. Now there are 3 situations that produce precipitation, and that's what we're going to go over for the rest of our time. The types of precipitation are orographic precipitation, frontal precipitation, and convection precipitation. Now, orographic precipitation is where we'll start, and that is precipitation that occurs as an air mass moves upward over mountains or mountain ranges. It comes from orography, oros meaning mountain, and graphy meaning description, as in geography. And orographic precipitation is common where mountain ranges rise close to the ocean or big lakes. And it's a little easier to visualize with a diagram. So if you look in your textbook on page 47, you'll see a diagram of orographic precipitation. And here's the air mass. It has water droplets in it because it's coming from an ocean or a lake. As it rises over the mountain, you can see it cools, forms clouds, there's condensation there, and the precipitation falls on the windward side of the mountain, and then by the time the air gets on the other side of the mountain, there's no precipitation left to fall. That's going to cause a dry climate on the east side of the mountain, which is known as a rain shadow. So you want to remember that term as well. It's going to come up. It's an area opposite the windward side of a mountain that usually receives little precipitation. And this is in the next chapter, but this gives us a good idea. You can see here the warm, wet air is coming up, the rain falls, the air's cool coming down, and there's no rain left. So we have a lot of vegetation on this side. Here is our rain shadow. Not much vegetation on that side. Okay? Then we also have frontal precipitation. And this occurs when 2 air masses meet. This is on your same page. A front is the line where the 2 air masses actually meet, and it's also known as cyclonic precipitation. It's common where warm air masses move in over bodies of water like the Gulf of Mexico or the Great Lakes. And this is also shown in your textbook on page 47. We can think of our cold air sinking as a mountain. The warm air rises over the cold air just like it does in our mountain precipitation, and then we have rain, and where the 2 meet is called our front. All right? Then we have convection precipitation, and this is precipitation when an air mass warms and rises rapidly, then cools to the dew point as it gains altitude. And it's common in the heart of North America. Again, it's easier to see with an illustration. What happens is the land cools at night, and then it heats again rapidly during the day. So the hot air is trying to rise, but it's trapped under the cold air from the evening. The hot air eventually breaks through the cold air, rises up really rapidly, it cools rapidly, and it drops water rapidly, often violently. So you have a thunderstorm type of rain with this convection precipitation. And that's going to wrap us up for today. So let's go ahead and look at your assignment. You need to read pages 44 through 47 to get all the little details about what we're talking about today. And then you want to backtrack and complete the section review thought question on page 45. We skipped that because we hadn't talked about ocean currents yet. Then go ahead and do your section review page on page 48. And you want to go ahead and get your activity 3-1, and you should be able to do number 1 at this time. As you read, think about this question. How would your life be different without the hydrological cycle? What benefits do you get from the hydrological cycle? All right, where in the world did you find the answer to our question? Where is one of the best known deposits of asphalt? In Pitch Lake on the island of Trinidad. And before next time, see if you can figure out the answer to this question. Where is the world's smallest official park?